In this video, we'll take a closer look at equilibrium calculations. Equilibrium constants can be used to calculate the concentrations of reactants and products that are present at equilibrium. The equilibrium constant is important because its magnitude tells you which substances predominate at equilibrium. For example, for equilibrium constants larger than 1, products will predominate at equilibrium. When an equilibrium constant has a value that is less than 1, reactants will predominate the equilibrium mixture. The law of mass action provides a general description of the equilibrium condition. For a chemical reaction mixture that is in equilibrium, the ratio between the concentration of reactants and products is constant. Using this hypothetical equation where substances A, B, C, and D represent chemical species and the lowercase letters E, F, G, and H are their coefficients in the balanced equation, the law of mass action is represented by the following equilibrium expression. K sub C is known as the equilibrium constant, and it is found by taking the product of the equilibrium concentrations of the products raised to their coefficients over the product of the equilibrium concentrations of the reactants raised to their coefficients. This problem asks us to calculate the value of the equilibrium constant. The following equilibrium concentrations were observed for the Haber process, which is the synthesis of ammonia. This reaction took place at 128 degrees Celsius. The equilibrium concentrations of the substances are as follows. For ammonia, 3.2 times 10 to the negative second molar. For nitrogen, 8.4 times 10 to the negative first molar. And for hydrogen, 3.2 times 10 to the negative third molar. Here is the balanced equation for the reaction at equilibrium, which we can tell by the double arrow. These are equilibrium concentrations that are given to us. That is very important because an equilibrium calculation has to have equilibrium concentrations plugged into the equilibrium expression before we can solve for K sub C. The equilibrium expression for this problem would be K sub C is equal to the equilibrium concentration of ammonia raised to the second power over the equilibrium concentration of nitrogen times the equilibrium concentration of hydrogen raised to the third power. And again, this expression is found by taking the equilibrium concentration of the products raised to their coefficients over the equilibrium concentration of the reactants raised to their coefficients. This is an equilibrium expression, so before we plug in any values, we need to make sure they are equilibrium concentrations. Taking the equilibrium concentrations that were given to us in the problem and plugging those into the equilibrium expression, we get this expression here. When we plug in the values and solve for K sub C, we find that the equilibrium constant for this reaction at this temperature is 37,000, which is rounded to 2 significant figures, and tells us that the mixture reaching equilibrium will contain mostly products. Notice there aren't any units listed for the equilibrium constant. Equilibrium constants are typically considered to be dimensionless quantities. Here's another problem that asks us to calculate the value of K sub C, the equilibrium constant. A system initially containing 2.00 times 10 to the negative third molar hydrogen and 4.00 times 10 to the negative third molar iodine at 388 degrees Celsius is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of the hydrogen iodide is 2.81 times 10 to the negative third molar. Calculate K sub C, the equilibrium constant, at 388 degrees Celsius for the reaction taking place, where the balanced equation shows for every 1 mole of hydrogen that reacts with 1 mole of iodine, 2 moles of hydrogen iodide are produced. Don't forget that this system is at equilibrium. We can use an ICE chart here, which is a tool for tabulating data from equilibrium problems. I stands for the initial conditions, C stands for the change in conditions, and E represents the equilibrium concentrations. And remember, to solve equilibrium constant expressions for the value of K sub C, we need to know these equilibrium concentrations. That's what we plug into the expression. We know that initially there were 2.00 times 10 to the negative third molar hydrogen, 4.00 times 10 to the negative third molar iodine, and we also know that at equilibrium, there's 2.81 times 10 to the negative third molar hydrogen iodide. So we know that the hydrogen iodide must have increased by 2.81 times 10 to the negative third. And the stoichiometry from the equation tells us that the hydrogen and the iodine must have decreased by half as much as the rate of appearance of the hydrogen iodide. And this coefficient of 2 tells us that 2 moles of the hydrogen iodide are being produced for every 1 mole of hydrogen that is consumed or every 1 mole of iodine that is consumed. And so that's how we came up with the values for the change in the concentration of the hydrogen and the iodine. They must have disappeared at half the rate that the hydrogen iodide appeared. So that's where we got a change in negative 1.41 times 10 to the negative third for both substances, the hydrogen and the iodine. So now we have everything we need to determine the equilibrium concentration of all three substances. Since the concentration of hydrogen is decreasing as the system approaches equilibrium, we take the 2.00 times 10 to the negative third and subtract 1.41 times 10 to the negative third, and we're left with 5.9 times 10 to the negative fourth molar. That is the equilibrium concentration of hydrogen. Since the concentration of iodine is also decreasing as the system approaches equilibrium, we take the initial concentration, 4.00 times 10 to the negative third, and subtract the change in the concentration of iodine, which was 1.41 times 10 to the negative third, and we find the equilibrium concentration of the iodine is 2.59 times 10 to the negative third molar. And we already have the equilibrium concentration of the hydrogen iodide, which is 2.81 times 10 to the negative third molar. Now we can solve for the equilibrium constant. Remember the equilibrium system. The equation was this: 1 mole of hydrogen plus 1 mole of iodine in equilibrium with 2 moles of hydrogen iodide. When we set up our equilibrium expression, we want the products raised to their coefficients in the numerator over the reactants raised to their coefficients in the denominator. But since both reactants have an understood 1 as coefficients, we just have hydrogen concentration times iodine concentration in the denominator. And remember, this is an equilibrium expression, so the only numbers that we can plug in here are those molar concentrations that are at equilibrium. So for the hydrogen, we take the 5.9 times 10 to the negative fourth and plug it in here. For the iodine, we take the 2.59 times 10 to the negative third and plug it in here. For the hydrogen iodide, we would take the 2.81 times 10 to the negative third and plug that in here. So when we plug those values into our equilibrium expression and solve, we find that the value of K sub C, our equilibrium constant, is 5.16, which tells us that the mixture reaching equilibrium will contain mostly products. Here's one for you to try. At a given temperature, the initial concentration of sulfur trioxide is 4 molar. The sulfur trioxide decomposes according to the reaction here. 2 moles of sulfur trioxide are in equilibrium with 2 moles of sulfur dioxide and 1 mole of oxygen. At equilibrium, the concentration of the sulfur trioxide is 2 molar. Calculate the equilibrium constant for this reaction. Press pause and give it a try, and then press play to check your work. Hopefully, the first thing that you set up was the equilibrium expression, which again is the products raised to their coefficients over the reactants raised to their coefficients. So this is the equilibrium expression for this equilibrium reaction. Then if you set up an ice chart, the information that was given to you was that the sulfur trioxide was initially at 4 molar, but at equilibrium it was 2 molar. So that means it must have changed, or the concentration must have decreased by 2 molar. And if we look back at the stoichiometry from the balanced equation, we see that the sulfur dioxide also has a 2. So that means that the sulfur dioxide was appearing at the same rate that the sulfur trioxide was disappearing, which is why we put a +2 for the sulfur dioxide. The oxygen has an understood 1 as a coefficient, which means it is appearing at half the rate that the sulfur trioxide is disappearing, which is why we put a +1 here for the change in the concentration of oxygen. And so now we have equilibrium concentrations for all 3 species, and we can plug these into our equilibrium expression to solve for K sub C. So for the sulfur dioxide, we took the 2 and plugged it in here, and we squared it based on the fact that there was a coefficient of a 2 in front of sulfur dioxide, which is why there was an exponent of 2 in the equilibrium expression. We multiply that times the concentration of the oxygen at equilibrium, which was 1. In the denominator, we took the sulfur trioxide concentration at equilibrium, which was 2, and we plugged that in and squared it as well. And when we did the math, we see that 2 squared is 4, times 1 is 4, divided by 2 squared, which is just 4. So what we are left with is 4 divided by 4, or in other words, the equilibrium constant had a value of 1, which tells us that neither reactants nor products predominate at equilibrium. And that's a closer look at equilibrium calculations. For more chemistry matters, go to our homepage where the entire series is available to you.